Here's 4.1 inverse functions. We're going to look at one-to-one functions, inverse functions, and equations of inverse functions. Okay, here we have a set of ordered pairs. So this is negative 2, 2, negative 1, 1, 0, 0, 1, 3, and 2, 5. So we can, by taking this set of ordered pairs, we can create an inverse to that. So I'm going to go ahead and write this. So we're going to call this set F, and this is negative 2, 2, negative 1, 1, 0, 0, 1, 3, and 2, 5. So these are our points, right? Ordered pairs. So the inverse, all we do for the inverse is we just take the x and y coordinates and we switch places. So what was the y is now x, and what was the x is now y, and we'll call that set G. So instead of negative 2, 2, we switch them, and now the inverse is 2, negative 2. And so instead of negative 1, 1, we switch it, and now the inverse is 1, 1. 1, negative 1 rather. 0, 0, well, you switch that and it's still 0, 0, right? 1, 3 becomes 3, 1. And 2, 5 becomes 5, 2. Okay, and so that's our inverse. So we use inverse functions to help us solve problems. In arithmetic, subtraction is the inverse operation of addition. Division is inverse operation of multiplication. So with functions, we can come up with an inverse, and we can use that to solve problems. So let's backtrack a little bit and let's look at what the definition is of a function. Okay, function, basically for each x there's and only one unique y, right? But we kind of put that definition in layman's terms, and we said for each x value there can only be one y value. So for each x there's only one y. Well, if you look here, for an ordered pair to be a function, the x values cannot repeat, because if they do, then they have more than one y value. So we got only one negative 2, only one negative 1. We look at the x values, only 1, 0, only 1, 1, 1, 2. So this is a function. This set of ordered pairs is a function. Now, before a function can be looked at to get an inverse function, you have to establish it as being 1 to 1. 1 to 1. So 1 to 1 takes the definition of a function and it makes it even more narrow in definition. So we said for a function, a relation to be a function, we said that for each x value there can only be one y. For each x value, there can be only one y value. I messed that up. So it takes the definition of a function and it goes further. For each x value, there's only one y value. And for each y value, there can only be one x. There can be only one x value associated with it. So for a function, for each x, there can only be one y. 1 to 1, for each x, there can only be one y. And for each y, there can only be one x. So in other words, in the set of ordered pairs, for a function to be 1 to 1, not only do the x values cannot repeat, the y values cannot repeat either. They could repeat in a function, but they cannot repeat if it's 1 to 1. So if you look here, because when you switch these numbers and the y is now the x value in the inverse, you want to see that the inverse is also a function. Well, there's only 1, 2, only 1, 1, only 1, 0, only 1, 3, only 1, 5. So the inverse, so in order for a function to be 1 to 1 and its inverse to be a function, you have to have the function be 1 to 1. Okay. So here we have a mapping diagram. Next, let's look at that. All right, we have a mapping diagram that's similar, and these are, this is domain and range. And domain, we've got 1, 2, 3, 4, 5, 6, 7, 8, and 9. Okay, so you have this 1 matches up with the 6, and so that's our function. So in other words, the input is a 1 and the output of this function is a 6. So in other words, we substituted 1 into the function, and the answer comes out as the result comes out as a 6. Next, we look at 2, and that's a 7. We put in a 2 and we get 7 out. Put in a 3, we get 7 out again. Put in 4 out, we get 8. Put in 5 and we get a 9. Well, for this mapping diagram, it cannot, in order for this mapping diagram to be a function, it cannot make like a V. In other words, the x value cannot have two y's. So it's a function, but is it 1 to 1? Well, in order for it to be 1 to 1, the x values can only have one y, and the y values, that cannot v out either. So the x, for a 1 to 1, the x can only have one y, and the y can only have one x. Well, the 1 has only one y, that's a 6. The 2 has only 7. And the 3 only has a 7. But the 7 has two x values, 2 and a 3. So because of that, this relation is a function, but it's not 1 to 1. So we would classify this as not 1 to 1. Okay, any questions there? Well, what does look like one-to-one? Well, let's look at another mapping diagram. And here's domain and range. In other words, the x values and the y values. And we have here 1, 2, 3, 4, and 5, 6, 7, 8. Okay, the 1 only has the 5. The 2 only has the 7. The 3 only has the 6. And the 4 only has the 8. Well, the 5 only has a 1. The 6 only has a 3. The 7 only has a 2. And the 8 only has a 4. So we can say that this not only is this a function, but it is one-to-one. Any questions with that? Okay. Next we can also test graphically. And we said that if we're looking at a graph, such as a parabola, and we wanted to see if that graph is a function, we could do we could go ahead and use the vertical line test. So with the vertical line test, wherever the vertical line is drawn, that line can only pass through the curve at one and only one point. So since this function has, no matter where you draw the vertical line, it passes through only one point, so we can say this is a function. But in order for it to pass, in order for it to test for one-to-one, we have to see if it can pass the horizontal line test as well. Well, the horizontal line test again, this time we draw a horizontal line, and no matter where we draw that horizontal line, it can only pass through one point. If it passes through more than one point, then it is not one-to-one. So because the horizontal line passes through more than one point, we would classify this as not one-to-one. Well, what looks like a graph that is one-to-one? Well, let's say that we had a graph that looks like this, like an x cubed. Y equals x cubed. Well, no matter where you draw that horizontal line, it's going to pass through only one point. No matter where you draw that horizontal line. So we can say that y equals x cubed is 1, 2, 1. Okay. And so that's the horizontal line test. And so that's what it says here in the PowerPoint notes. A function is one-to-one if every horizontal line intersects the graph of a function at most one point. Okay. So, any questions with that? All right. Let's see. So let's review what we know so far. In order for a function to be 1 to 1, in a set of ordered pairs the x values do not repeat, and the y values do not repeat. Okay, the next thing is a mapping diagram. And we said in a mapping diagram, the x values do not form a V, do not form a V when they're matching up between the x and y values, and the y values do not form a V either. Okay. And then the third thing that we looked at was the horizontal line test, graphing. And so we used the horizontal line test We used the horizontal line test where the line passes through the graph at only one point. No matter how many lines you draw, that line will pass through the graph at only one point. Okay. And there's one more that we haven't looked at yet, but I'll go ahead and write it on here. Equations. And in equations, in order for it to be 1-to-1, we cannot have x squared, or we can have an x squared, but we cannot have a y squared. Cannot have a y squared, and cannot have a plus or minus a radical expression, because that's basically the same thing as y squared if you were to solve for it. Anything else that we're looking at can be, in order for it to be 1-to-1, it can be a function. It can be 1-to-1. All right, so an inverse function the function that f is 1-to-1 defines the inverse function is essential. Otherwise, the inverse will not define a function. So special notation for inverse function is where f as a function is you use f with a raised -1, and this is known as f inverse. It's not the reciprocal, it's the inverse function. So like this one here, the function for f of x equal to x cubed minus 1, the inverse is, this would be known as the inverse function is cube root of x plus 1. So that would be the annotation for inverse function. Okay, so this -1 here, that's not considered an exponent. Okay, that's not an exponent. That signifies when it's a -1 in the function side, then it's not an exponent. Okay. All right. So, all right. So let's take a look at set of ordered pairs again. So we're going to look at our set of ordered pairs for -2, 1, -1, 0, 0, 1, 1, 2, and 2, 2. So let's see. Is this first of all, is this a function? There's only one -2, only one -1, only one 0, 1, 1, 2. So it's a function. Let's see if it's 1 to 1. So the x's do not repeat. Let's see if the y's values do not repeat either. Well, there's 1, 0, 1. Okay, so the y's do repeat, but the x values do not. So it's a function, but it's not 1 to 1. All right, so this is a function, but it is not 1 to 1. All right, any questions with that? And all it takes is one of them to repeat. So not only the ones repeat, but the twos also, there's two y values that repeat. Okay, so let's look at another one. All right, here we have G. We'll call this G. And we've got here 3, 1, and 0, 2, and 2, 3, and 4, 0. All right, so this is a function, but let's see, is this a function? Only 1, 3, 0, 2, 4. So it's a function, but let's see if it's 1 to 1. So we check the y values. Do they repeat? 1, 2, 3, 0. Okay, the y values do not repeat. The x values do not repeat. So we can say, yes, this is 1 to 1. So we can proceed from there and find the inverse to this function. So all we do is we take the x and y values and we switch them. Actually, I'm going to do this in black because I want to show you something. All right, so 3, 1, we switch it. Now it's the inverse is 1, 3. 0, 2, we switch that. The inverse is 2, 0. 2, 3, switch it. It's 3, 2. 4, 0 is 0, 4. Okay, let's look at the domain and range. Domain are all the x values. So it's 3, 0, 2, 4. 3, 0, 2, 4. The range are all the y values. 1, 2, 3, 0. So that would be 0, 1, 2, 3. Okay, now let's look at the domain and range for our inverse. Again, domain are all the x values. 1, 2, 3, 0. So that'd be 0, 1, 2, 3. And the range are all the y values. 3, 0, 2, 4. So that'll be 0, 2, 3, 4. Okay, so 0, 3, 2, 4. What's the domain is the range. What is the domain for the function is the range. So actually, let's change this 0, 2, 3, 4. 0, 2, 3, 4. Put those in order. Okay, same number, so just switch the order in it. 0, 2, 3, 4, 0, 2, 3, 4. What was the range in the function is the domain in the inverse. Because we switch each x and y coordinate, the domain and range switch as well. Okay, so that's domain and range for or set of ordered pairs. All right, moving on. Let's look at how we can, the steps that are used to find the inverse equation. Okay, for a one-to-one function, f defines an equation, y equals f of x. Find the definition equation of the inverse as follows. Step 1. I'm going to go even further than that, and I'm going to say change, if needed, change y to f of x. Step 1, change f of x to y. So if you have a function that has f of x in it, you change it to y, because y and f of x are synonymous, right? They're equal statements. Step 2, exchange x and y values. Exchange x and y variables. So what was y is now x, and what is x is now y. And then step 3, solve for y. And then step 4, replace y with the inverse function sign. Okay, so let's take a look at an example. Here we have f of x is equal to 2x plus 5. All right, so first thing we're going to do is change f of x to y. So now f of x is y, becomes y, so this is y equals to 2x plus 5. And now the next step is exchange the x and y variables. So what is y is now an x, and what is x is now a y. So it's now x equal to 2y plus 5. And then now we're going to solve for y. So to solve for y, we apply a minus 5, the additive inverse, so the 5's go to 0, right? They cancel out. And so we get x minus 5 equals to 2y. Well, what do we do with that 2? We got to make that 2 go to 1 by dividing both sides by 2. So the 2's cancel out, they divide out, they go to 1. So now I'm going to switch this y over to the left side. We can do that. Y equals to x. And then I'm going to split this. X over 2 minus 5 over 2. We can do that. Because if we had 1/2 plus 1/2, that's 1 plus 1 over 2, right? That's 2 over 2. So we can combine fractions and we can also split them. Okay, so that's what we're doing here. And so we change y to our inverse function sign, the inverse, and we can make this is 1 over 2, 1x over 2, so we can change that to 1/2 x, because that means the same thing, minus 5/2. Well, why would I split it like that? Because sometimes if you can simplify it, you can simplify it more easily this way. And so this is our inverse function. All right. Okay. Well, so the solution of equation, all right, so let's try another one. Let's say that we have here y equals 2x squared plus 2. And we want to decide whether the equation defines a one-to-one function. So if we were to find the inverse, then the inverse should be a function as well. So we switch x and y. So what is y is now x, and what is x is now y. So this becomes x equal to y squared plus 2. And we subtract 2, or apply, I like to say apply minus 2 to both sides. So we get x minus 2 equals 2y squared. And then we have to get rid of that square. Well, the inverse of square is square root. So we apply a square root, but we have to put a plus or minus. So we can switch that. So this is y equals to plus or minus the square root of x minus 2. And remember I said before that if it has a plus or minus in it, then we cannot, that's not a function. I mean, that's not one-to-one. So this is the inverse is not a function. And so this is not 1 to 1. Okay, not 1 to 1. Okay. And so you could also graph this as a parabola. And this is 2. So we can see that this would not pass the horizontal line test, and so we could also tell that this is not 1 to 1 either. Okay. So what about something like this where we have f of x equals 2x minus 2 parentheses q. Well, I mean, you could graph this. So this is going to behave like an x cubed, right? Up and to the right, down and to the left. And this is going to, because it's inside parentheses, it's going to shift right 2 spaces. So this will be like that. And so if we were to take the horizontal line test, you could see that it would pass the horizontal line test. And so we could say, yes, this is 1, 2, 1. Okay. And so there's another way to do that. Okay, let me see if there's anything on the homework we need to go over. Well, let's go over how to find the inverse of this function, because that is on the homework. Okay, so let's say we wanted to find the inverse. So f of x equals 2x minus 2 quantity cubed. So we replace f of x with y. So y equals 2x minus 2 cubed. And now we switch x and y. So what is y is now x, and what is x is now y minus 2 cubed. Okay, well, first thing we have to do is get rid of that exponent. So we apply not square root, but a cube root. Apply cube root. And with the odd roots, you don't have to apply plus or minus. It's only the even roots. So there's no plus or minus there. So this is the cube root of x equals to, and we can go ahead and get rid of the parentheses, y minus 2. Now all we do is just apply a plus 2 to both sides. Plus 2 plus 2. So that gives us the cube root of x plus 2 equals 2y. And notice this is not underneath the radical. Okay? And so now we can switch that and say, all right, y equals 2 cube root of x plus 2. And so change y to the inverse of function of f equals to x cubed, the cube root rather, plus 2, and that's our inverse function. All right. Let's see if there's anything else there. It's kind of all right. One more. What if we have a rational function? Such as f of x is equal to 8 over x plus 8. Okay, we change f of x to y. Y equals to 8 over x plus 8. Now, the first thing I've always said in the past, and now we've got to change x and y values, right? So what was y is now an x, and what was an x is now a y. So this is x equal to 8 over y plus 8. And then now we have to solve for y. Well, the first thing I've always said we've got to do is get rid of the denominator. So this would be considered parentheses here. So we got to multiply out the denominator by multiplying both sides by y plus 8. So we multiply y plus 8. Be sure to use parentheses. So the y plus 8s, they cancel out, they go to 1. Here we have to go ahead, because we have to solve for y, we got to go ahead and distribute that x. So this becomes xy plus 8x equals to 8. Now we can have to continue to solve for y. So we apply minus 8x minus 8x, and we get xy is equal to a negative 8x plus 8. And now we're going to divide. We got to isolate that y further, so we got to divide by x. Divide by x. Now, the answers the book gives, the homework gives, does not split the x this time. So the x's cancel, right? They go to 1. So we get y equals to negative 8x plus 8 over x. So we change that y to the inverse of f, and that's our answer. So whatever this, if we start with f of x, then the inverse is going to be the inverse function of f. If it's g of x, it starts off with g of x, then it'll be g inverse of g of x. If it's h of x and so on, it'll be inverse of h of x. Okay, and so we don't have a plus or minus square root, right? So we can say that this is in fact 1 to 1. All right, and that's all there is to this lesson, and have a good day.